Hey everyone, today we're tackling a Leetcode problem called maximum value of an ordered triplet I. It sounds a bit fancy, but we'll break it down together, step by step. The goal is to find the biggest possible score from picking 3 numbers in a list, following a specific rule. Let's dive in. Alright, here's the official description. Don't worry about reading all the text. The main idea is this. You get a list of numbers. You need to find 3 positions in the list. Let's call them I, J, and K. These positions must be in increasing order. So comes before and comes before. For each set of 3 like this, you calculate a value. Take the number at position, subtract the number at position, and then multiply the result by the number at position. Your job is to find the triplet, I, J, K, that gives the absolute biggest value. If all possible triplets give you a negative value, the answer should be 0. Let's walk through an example. Suppose our list is 12, 6, 1, 2, 7. We need to find I, J, and K such that I less than J less than K. Let's try picking I equals 0, J equals 2, and K equals 4. Are they in order? Yes, 0 is less than 2, and 2 is less than 4. Now let's grab the numbers. The number at index 0 is 12, at index 2 is 1, and at index 4 is 7. The formula is number at I, number at J, times number at K, so that's 12 to 1, times 7. This equals 11 times 7, which is 77. It turns out, for this list, 77 is the highest value we can get, so the output is 77. Okay, what's the most straightforward way to solve this? We could just try every single possible combination of I, J, and K that fits the rule, I less than J less than K. We can use 3 loops. The first loop picks the second loop picks starting from, and the third loop picks starting from. Inside the innermost loop we calculate the value, nums. Bits We'll keep a running maximum, updating it whenever we find a bigger value. Finally, since the answer must be at least 0, we return our maximum value found. This works, but using 3 nested loops is usually slow if the list is long. We call this O of n cubed complexity. We can probably do better. Let's think about the formula. Nums. To make this large, we ideally want nums to be big, nums to be small, and nums to be big, assuming the difference nums is positive. Consider fixing the middle index j. To maximize the result for this specific j, what's the best I we could pick? We should pick the I before j that has the largest nums. Similarly, what's the best k? We should pick the k after j that has the largest nums. This gives us an idea. Maybe we can pre-calculate these maximums? So let's try this. We can make 2 extra lists. The first list, let's call it max_left, will store, for each position j, the biggest number found in the original list, before position j. The second list, max_right, will store the biggest number found after position j. We can calculate these 2 lists in a couple of passes through the original numbers. Once we have them, we can loop through all possible middle positions j, from index 1 up to n2. For each j, we look up the pre-calculated max_left and max_right. Then we calculate max_right, and update our overall maximum result if this value is bigger. Remember to ensure the final result isn't negative. Here's the code for the prefix/suffix max approach. First, we handle the case where the list is too short. Then, we create the max_left array. We loop from the second element, keeping track of the maximum number seen so far, and storing it in max_left. Next, we do a similar thing for max_right, but we loop backwards from the second to last element. Finally, we loop through the possible middle indices j. Inside the loop, we grab the precomputed max_right, and max_right. We calculate the triplet value using these and nums. We only consider it if the left maximum is actually greater than the middle number. Otherwise, the difference, max_left nums, would be 0 or negative. We update our overall max_value and return it at the end. This is much faster, about O of n time, but it uses extra memory for those 2 arrays, O of n space. Now, can we be even smarter and use less memory? Maybe we don't need those extra arrays. Let's think about iterating through the list just once. Imagine we are currently looking at the number at index j. What information do we need from the elements before j to calculate the best possible triplet value that could use nums as the third element, chi equals j? If nums is our nums, we need to have already found the best possible nums, where both I and mid came before j. Let's keep track of two things as we loop. First, the maximum number encountered so far. Let's call this max_i. This represents the best possible nums we could use. Second, the maximum difference, max_i, nums, encountered so far. Let's call this max_i when we're at index j, considering nums as nums. The best possible triplet value ending here is max_i diff nums. We update our overall answer with this if it's larger. Then, we update max_diff using the current max_i and the previous element nums, acting as nums. And finally, update max_i using nums. This sounds a bit tricky. Let's see the code. Okay, let's look at this optimized code. We initialize our result res to 0. We also need max_far, which will track the maximum number seen up to the point before the current number, and max_diff_far, which tracks the maximum difference, max_far, some previous number. We loop through each num in the list. Inside the loop, first, we consider the current num as the potential nums. The best result we could get ending here is the max_diff_, so far we've calculated from previous steps, multiplied by the current num. We update our overall res if this is bigger. Then, we prepare for the next iteration. We update max_diff_, far, by seeing if the difference between the previous max_far and the current num treating current num as nums is better than the existing max_diff_, far. Finally, we update max_far by comparing it with the current num, treating current num as a potential nums for the future. This single pass gets the job done. So how do these approaches stack up? The brute force method is simple to think about but slow, taking n³ time. The prefix/suffix maximum approach is much faster, order n time, but it needs extra order n space for those helper arrays. The final optimized greedy approach is the winner. It runs in order n time, just like the prefix/suffix method, but it only uses a constant amount of extra memory, order 1 footspace, regardless of how big the input list is. That's really efficient. Alright, let's recap. We needed to find the maximum value of nums for I less than j less than k. We saw that a simple brute force check is too slow. Thinking about maximizing the components led us to the prefix/suffix maximum idea, which was much faster but used extra space. The most clever solution involved a single pass, keeping track of the maximum element seen so far, and the maximum difference, max_element, current_element, seen so far. This gave us the best time and space complexity. And don't forget, if all calculations result in negative numbers, the answer is 0. Hope this explanation helped you understand the problem and the different ways to solve it. If you found this useful, you know what to do. Like, subscribe, leave a comment, maybe even buy me a boba. Keep practicing and see you next time.